Hello there, and welcome to the Sleep with Science channel. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps the channel to reach more curious minds like yours. Now let's begin. Close your eyes for a moment, and imagine a light leaving home 4 years before it reaches you. Not 4 minutes, like sunlight on your skin. Not 4 hours, like whispers from the edge of our solar system. 4 years. That is the strange, patient distance between us and Alpha Centauri, our nearest stellar neighbor, and it is exactly where our story begins tonight. Because recently, humanity's most powerful eye ever built, the James Webb Space Telescope, turned its golden hexagonal mirrors toward that very system. And what it gathered, in the quiet language of infrared light, has left astronomers speaking carefully, cautiously, choosing their words the way you might choose your steps in a dark and unfamiliar room. Something about that light didn't behave the way it should have. Something about the space around those 3 stars felt, to the instruments, different. Not broken. Not dangerous. Just different enough to notice. Different enough to make seasoned scientists pause, lean back in their chairs, and look again. Tonight, we are not here to frighten you. We are here to wonder with you, slowly, the way the universe itself unfolds, one photon at a time, one heartbeat at a time. So let your shoulders soften into whatever surface is holding you right now. Let your breathing slow, in through the nose, out through the mouth, like a tide pulling gently away from shore. Because where we're going tonight, you won't need urgency. You'll need patience. You'll need the kind of stillness that lets you hear what has been circling quietly around one of the most studied star systems in the night sky. Alpha Centauri is not one star. It is 3, bound together by gravity in a slow cosmic dance older than our own species. Alpha Centauri A golden twin to our Sun, slightly larger, slightly brighter, burning with the same steady warmth that allowed life to take root on Earth. Alpha Centauri B, smaller, cooler, more orange in hue, orbiting its sibling in a rhythm that takes about 80 years to complete, a full human lifetime measured in a single revolution. And then, hanging at the outskirts of the stellar family, small and dim and easy to overlook, Proxima Centauri, a red dwarf so faint that it wasn't even discovered until 1915, despite being, in cosmic terms, right next door. For over a century, we have watched this system the way you might watch a familiar house across the street, comforted by its predictability. We catalogued its stars. We measured their masses, their temperatures, their orbits. We found planets there, small rocky worlds tucked close to Proxima, one of them sitting inside what scientists call the habitable zone, that delicate strip of space where water could exist as liquid rather than ice or vapor. We named it Proxima Centauri b, and for years it lived quietly in our imagination as perhaps the closest thing to another Earth we may ever find. But familiarity, as it turns out, is not the same as understanding. And that is the thread we are going to follow tonight, gently, unhurriedly, the way starlight itself travels, patient across the dark. Because when James Webb pointed its infrared instruments at this system, it wasn't looking for what we already knew. It was listening for what we didn't. Webb doesn't see the universe the way our eyes do, the way old telescopes once did, catching only visible light bouncing off distant surfaces. Webb feels heat. It reads the faint thermal signatures of dust, of debris, of things too cold and too dark for ordinary sight. It can detect a temperature difference smaller than a fraction of a degree, from a distance of 25 trillion miles. And in that heat signature, in that quiet infrared hush surrounding Alpha Centauri, something appeared that shouldn't have been there. Or perhaps, something failed to appear that should have. The astronomers reviewing the data used a word that doesn't often make it into press releases: anomalous. Not dangerous. Not explained. Simply anomalous. We will get there. We will walk through exactly what Webb detected, what it means, and why some researchers have quietly begun rechecking their calibrations, running the numbers twice, 3 times, unwilling to publish until they are certain they aren't imagining a shadow where none exists. But first, let yourself sink deeper into this moment. Let the weight of your body settle further into rest. Because to understand what Webb found circling our nearest stars, we first need to understand something more fundamental about starlight itself, about how it bends, how it lies, how it carries secrets across the dark for years before anyone thinks to ask the right question of it, and how 4 years ago, something out there may have already changed. Starlight is not simple. It is not just a beam traveling in a straight, unbroken line from a distant furnace to your eye. It bends. It stretches. It gets pulled and pinched by gravity, scattered by dust, filtered by the thin veils of gas that drift between the stars like curtains in an empty house. By the time light from Alpha Centauri reaches Webb's mirrors, it has already been shaped by everything it passed through. And so, before we can understand what the telescope found, we need to understand this one truth, held gently in your mind like a small stone in your palm. What we see is never quite what is. It is always a translation. Always a story arriving late, and slightly changed by its journey. Let your breathing settle further. In slow and out, slower still. There is no need to hurry toward answers tonight. The universe has waited over 4 years for this light to arrive. It can wait a little longer for us to understand it properly. James Webb was never built to simply take pretty pictures of the cosmos, though it has given us many. It was built to solve a very specific kind of problem, one that had frustrated astronomers for generations. Visible light, the kind our eyes evolved to see, is easily blocked. Dust clouds, planetary debris, the glare of a nearby star, all of these can hide things from ordinary sight the way fog hides a lighthouse. But heat cannot hide so easily. Infrared light, the invisible radiation just beyond the red edge of the rainbow, slips through dust like a whisper through a cracked door. It reveals what visible light conceals. And Alpha Centauri, brilliant as it is in our night sky, has always been surrounded by exactly this kind of concealment, faint disks of debris, unseen companions, the quiet architecture of a young solar system in its slow, patient formation. When Webb was aimed at this system, the goal, at least officially, was modest. Astronomers wanted to search for warm dust, the kind that might indicate the presence of undiscovered planets or debris left over from the system's formation billions of years ago. This is delicate work. Alpha Centauri A is so bright, and so close to us in cosmic terms, that studying anything faint near it is like trying to see a firefly hovering beside a lighthouse. Engineers had to use a specialized technique, a kind of light-blocking mask called a coronagraph, to suppress the glare of the star itself, allowing the far dimmer details around it to emerge from the darkness. It is a technique that requires extraordinary precision, canceling out billions of photons from a star while preserving the handful of photons carrying real information. And for a while, the data looked exactly as expected. A faint smudge of warmth here. A gentle gradient of dust there. The quiet, unremarkable signatures of a mature stellar system going about its ancient business. Nothing alarming. Nothing that broke from the models built over decades of study. If anything, it was almost comforting, this predictability written in infrared light. But then, in a region of the data that should have shown a smooth, gradual fall-off of warmth, the kind of steady decrease you would expect as you move outward from a star into the growing cold of space, the researchers found a gap. Not an object. Not a clear structure, glowing and defined. Something more elusive than that. A break in the pattern. A place where the numbers simply did not behave the way 60 years of astrophysical modeling said they should. Let that settle over you slowly, the way snow settles over a quiet field, without urgency, without alarm. We are not speaking of danger. We are speaking of a puzzle, the kind the universe offers us often, if we are patient enough to notice it. Because space, despite its silence, is rarely empty of surprises. Every time we build a more sensitive instrument, every time we listen a little more closely, the cosmos seems to answer with something we did not expect. This has always been true. It was true when we first pointed telescopes at Jupiter and found moons where none should exist. It was true when we first split starlight into its component colors and discovered that stars are made of the same elements as our own bodies. And it may be true again now, in this quiet gap of infrared data circling our nearest stellar neighbors. Rest here for a moment. Let your mind drift, unhurried, over the vastness of that 4 light-year distance, the sheer scale of space between us and Alpha Centauri, a gap so wide that even light, the fastest thing in existence, needs years to cross it. And somewhere within that gap, within that quiet stretch of starlit dark, something was recorded that does not yet have a name. Something the data insists is there, even though no model predicted it, even though decades of careful observation of this very system gave no warning that it was coming. To understand what that gap might mean, we first have to go back further still, to the very beginning of how Alpha Centauri came to be studied at all, and why 3 points of light in the southern sky captured human imagination. Long before we had the instruments to understand what we were truly looking at. Let your body sink a little deeper now, into the soft weight of rest. There is nothing to solve tonight, nothing to hold on to tightly. Just the slow unfolding of a story written in starlight, one gentle word at a time. Alpha Centauri has always held a peculiar magnetism over the human imagination, long before telescopes, long before satellites, long before anyone understood what a star truly was. To ancient skywatchers in the southern hemisphere, it was simply one of the brightest points in the night, a steady beacon low on the horizon, woven into stories passed down through generations who had no way of knowing it was not 1 light, but 3. The people of the Southern Cross traditions saw it as a guide, a companion to the constellation beside it, a fixed point in an otherwise shifting sky. It would be centuries before anyone suspected that this single brilliant point was actually a pair of suns locked in a slow gravitational embrace, with a third, fainter star drifting nearby, unseen by the naked eye. It was in 1689 that a Jesuit astronomer, observing from the Cape of Good Hope, first noted that Alpha Centauri appeared to be a double star, 2 points of light so close together that ordinary eyes blurred them into one. This was startling, in its own quiet way. It meant that what looked like a single simple star was, in fact, a system, 2 massive bodies of golden and orange fire, wrapped in gravity, spinning around a shared center of mass, invisible to anyone without a telescope. And even then, it would take more than 2 centuries for the third member of this family to reveal itself, the small, dim red dwarf we now call Proxima Centauri, discovered only in 1915 by the Scottish astronomer Robert Innes, working from an observatory in South Africa. Think, for a moment, about the quiet strangeness of that timeline. For nearly all of recorded human history, we lived beneath a sky that contained our nearest stellar neighbors, and we did not know it. Proxima Centauri had been shining faithfully, steadily, for over 4 billion years, its light reaching Earth every single night, and yet it remained invisible to us, hidden not by distance, but by its own dimness, until the right instrument and the right patient eye finally found it. This is the pattern that seems to repeat throughout the history of astronomy. The universe does not hide its secrets out of malice. It hides them simply because we have not yet learned how to look closely enough. And every new tool we build, every new way of seeing, seems to fold back one more layer of that hidden truth. Rest here a while. Let the rhythm of this story settle into you the way a lullaby settles into a sleepy child's mind, familiar, soothing, safe. Because what comes next in our story is simply another chapter in that same long pattern, another layer folding back beneath a newer, sharper eye. By the time the 20th century gave way to the 21st, Alpha Centauri had become one of the most thoroughly studied star systems in the sky, precisely because of its closeness to us. Every new generation of telescope, every advance in spectroscopy, every refinement in how we measure the wobble of starlight, was turned toward this nearby system almost as a matter of course. It became, in a sense, humanity's cosmic proving ground, the place where we tested our new tools first, because it was near enough to yield clear answers, and familiar enough that any surprises would stand out clearly against the well-mapped background we already understood. This is precisely why the recent findings from James Webb feel so unusual to the scientists studying them. This is not some newly discovered, distant, poorly understood corner of the galaxy, where anomalies might simply reflect our own ignorance of basic parameters. This is Alpha Centauri. This is the system we know best, after Proxima Centauri's discovery in 1915 rounded out a picture that astronomers spent the following century refining, measuring, and confirming across generation after generation of careful observation. Its masses are known. Its orbits are calculated with extraordinary precision. Its age, its composition, its likely history of formation, all of it has been studied more thoroughly than almost any other stellar system beyond our own Sun. And so, when something appears in the data that does not fit the models built not on speculation, but on more than 3 centuries of accumulated observation, it carries a different kind of weight than a strange signal from some anonymous, distant star we barely understand. It is less like finding an unexpected shadow in an unfamiliar room, and more like walking through your own childhood home in the dark, a house you have walked through 1,000 times, and suddenly finding a door where you were certain, absolutely certain, that only a solid wall had always stood before. Let that image rest with you for a moment. A familiar house. A door where a wall should be. Not frightening, not yet, just quietly impossible, the kind of impossible that makes you stand still in the dark and simply breathe, waiting for your eyes to adjust, waiting for the shape of things to make sense again. Let your own breathing follow that same rhythm now. Slow. Unhurried. In and out, like tide water easing over sand. There is nothing here that requires your alertness, only your attention, soft and unforced, the way you might listen to rain falling somewhere far outside a window. To understand why this particular anomaly troubled the researchers so deeply, we need to understand what Webb was actually measuring, and why the instrument itself represents such an extraordinary leap beyond anything that came before it. The James Webb Space Telescope does not orbit close to Earth, the way so many satellites do, circling us every 90 minutes in a tight, familiar loop. Instead, it sits nearly 1,000,000 miles away, at a gravitational balance point called the second Lagrange point, a place where the pull of the Sun and the pull of the Earth combine in such a way that a spacecraft can hover there with minimal fuel, staying in a stable, quiet position relative to both. From this distance, 4 times farther than the Moon, Webb keeps its enormous sun shield, 5 layers thin, each no thicker than a human hair, angled perfectly to block the heat of the Sun, the heat of the Earth, and the heat of the Moon, all at once. This is not a small engineering achievement. It is one of the most delicate balancing acts ever attempted in the history of spaceflight, because Webb's entire purpose depends on being cold. Achingly, precisely cold. Its mirrors and instruments operate at temperatures near -370 degrees Fahrenheit, only a handful of degrees above absolute zero, the theoretical limit at which all atomic motion stops entirely. This extreme cold is not incidental. It is essential. Because Webb is built to detect infrared light, the faint heat signatures radiating from distant objects, and if the telescope itself were warm, its own heat would flood its sensors with noise, drowning out the whisper-faint signals arriving from trillions of miles away. It would be like trying to hear a single distant voice while standing beside a roaring engine. So every part of Webb has been engineered to stay silent, to stay cold, to stay perfectly still, so that it might hear the universe's quietest secrets. And it is this extraordinary sensitivity that made the Alpha Centauri observation possible in the first place. Webb's coronagraph, the light-blocking instrument used to suppress the overwhelming glare of the two bright central stars, allowed astronomers to study the faint infrared glow immediately surrounding them, glow that would otherwise be utterly lost in the brilliance of Alpha Centauri A and B. This is delicate, exacting work. To block a star's light by a factor of 10,000, and still preserve the faint infrared traces of anything orbiting nearby, requires precision measured in nanometers, adjustments smaller than a single wavelength of light. It is the kind of task that, only 2 decades ago, would have been considered nearly impossible. Let your mind drift over that scale for a moment. Nanometers. A wavelength of light. The kind of precision so fine that human hands cannot achieve it directly, only through decades of careful design, careful testing, careful patience. And it is precisely this kind of patient, meticulous engineering that revealed the gap in the data, a space where the expected thermal signature simply did not behave as 60 years of prior study said it should. Rest a little deeper now. Let your shoulders soften further into whatever is holding you, the mattress, the couch, the quiet weight of your own tiredness. Because the story ahead requires no urgency from you, only your presence, only your willingness to listen as the picture slowly comes into focus. When the initial data came back from this observation, it passed through the hands of several independent research teams, each one responsible for verifying different aspects of the calibration, the pointing accuracy, the noise reduction, the countless small corrections that must be applied before raw telescope data becomes something scientists can trust. This is normal. This is expected. Every Webb observation goes through weeks, sometimes months, of this kind of careful, unglamorous verification before anyone is willing to say with confidence that what they are seeing reflects something real, rather than some artifact of the instrument itself, some flaw in calibration, some trick of light bouncing where it should not. And for most of that verification process, the Alpha Centauri data behaved exactly as such data should. Small inconsistencies were found and corrected. Familiar noise patterns were filtered out. The picture grew cleaner, sharper, more reliable with each pass. But one particular feature, small, faint, easy to overlook amid the vast river of numbers pouring in from the telescope's instruments, refused to resolve into something ordinary. No matter how many times the pipeline was run, no matter how many different algorithms were set loose upon it, that one faint point of light kept insisting on its own existence. It sat there in the data like a held breath, stubborn and quiet, refusing either to vanish as noise should vanish or to announce itself as something certain. This is the strange threshold where astronomy stops being a matter of seeing and becomes a matter of believing, carefully, provisionally, the kind of belief that scientists hold the way you might hold a soap bubble, aware that too firm a grip destroys the very thing you are trying to examine. Alpha Centauri is not a single star pretending to be one. It is a system of 3, bound together across billions of years by gravity that never lets go. Alpha Centauri A and B circle each other in a slow gravitational dance, 2 stars not unlike our own Sun, one slightly larger and hotter, one slightly smaller and cooler, separated by a distance roughly comparable to that between our Sun and Saturn. And somewhere out in the darker reaches, much farther still, drifts Proxima Centauri, a dim red ember of a star, so faint it was not discovered until the 20th century, so close in cosmic terms that its light takes barely 4 years to reach us, and yet still utterly beyond the reach of any spacecraft we have built or dreamed of building within a human lifetime. 4 decades, this system has occupied a peculiar place in the human imagination. It is close enough to feel almost like a neighbor, near enough that its light has touched Earth for the entire span of recorded civilization, and yet it remains, in the truest sense, unreachable. No probe, no signal, no borrowed light from our own instruments has ever crossed that gulf and returned. Everything we know about Alpha Centauri, we know only by watching, by measuring the faintest disturbances in light across 4 decades worth of empty space, translating photons into knowledge the way a blind man might read a language pressed into paper. It was this closeness, this deceptive, teasing nearness, that made Alpha Centauri a natural target when astronomers turned Webb's most sensitive coronagraphic instruments toward it. A coronagraph is a strange and delicate tool, essentially a shield built to block out the overwhelming light of a star so that anything hiding nearby, a planet, a disk of dust, the faint gravitational leftovers of a system's formation, might have a chance to be seen at all. Stars are staggeringly brighter than the worlds that orbit them, sometimes by factors of billions, and picking out something planet-sized beside something star-bright is a little like trying to notice a firefly hovering beside a lighthouse from several miles away, at night, through fog. In the earlier data from this same target, astronomers had already caught glimpses of something unusual, a source of infrared light sitting close to Alpha Centauri A, within roughly the same distance that Earth orbits the Sun. It was not something anyone rushed to call a planet. Real science does not work that way, however tempting the narrative. Instead, it was catalogued honestly as a candidate, a signal that could, in principle, be explained by several different things: a planet reflecting and re-emitting the star's warmth, a transient clump of dust caught in the star's gravitational grip, or simply a subtle imperfection in the way the coronagraph handled the ferocious brightness it was built to suppress. Every one of these explanations was plausible. None of them could be ruled out. And so the signal persisted in scientific limbo, neither confirmed nor dismissed, a shadow at the edge of certainty. What made the newest observation different was not that it repeated this same finding cleanly, but that it echoed it strangely, showing the same rough location, the same suggestion of faint infrared warmth, yet shifting slightly in ways that did not perfectly match what a stationary background object or simple instrumental artifact would produce. If it had been dust alone, models predicted a certain pattern of movement, or the lack of it, as the material drifted under gravity's slow pull. If it had been a planet, the physics of orbital motion offered its own precise, testable predictions. What the researchers found instead sat uncomfortably between these possibilities, matching neither model as cleanly as they had hoped, resisting the tidy categorization that would let anyone write a confident sentence and move on. This is the part of scientific discovery that documentaries rarely linger on, because it lacks the satisfying shape of a revelation. There was no triumphant image, no unmistakable ring of a planet crossing starlight, no signal that screamed its nature plainly across the electromagnetic spectrum. There was only this: a small, faint anomaly, sitting at the ragged edge of what the instrument could measure, behaving in a way that fit no existing explanation perfectly, forcing the very people who had built their careers on interpreting Webb's data into a place of humility they had not expected to occupy so soon. And so, rather than rushing to publish something bold, the teams did what careful scientists do when the universe refuses to answer cleanly. They began, once more, from the beginning. They returned to the raw exposures, the untouched frames captured long before any correction had been applied, and they asked the most basic question a scientist can ask: what, exactly, are we looking at, stripped of every assumption we have already made? This is a kind of humility that does not come naturally to any of us. We are pattern-seeking creatures. We want the dot of light to be something. We want the anomaly to resolve into a story we can tell around a fire, a planet, a mystery, an answer. But good science, the kind that survives scrutiny for decades rather than collapsing under the next observation, requires a willingness to sit inside uncertainty far longer than feels comfortable. So the researchers slowed down. They cross-referenced the position of this faint signal against every known catalog of background stars and galaxies, the countless faraway points of light that, from Earth's vantage point, might simply happen to line up behind Alpha Centauri by pure chance, a trick of geometry rather than physics. This is not a small concern. The sky is vastly more crowded than it appears to the naked eye. Even a patch of darkness the width of a fingertip held at arm's length can contain thousands of unseen background galaxies, their light bent and dimmed by unimaginable distance, and any one of them, positioned just so, could masquerade as something orbiting a nearby star when it is, in truth, sitting billions of light-years farther away, utterly unrelated, a coincidence of sightlines rather than a companion. They checked, too, for the subtle fingerprints of instrumental scatter, the way starlight, even when suppressed by a coronagraph as sophisticated as Webb's, can still leak faint traces of itself into unexpected places, bouncing off tiny imperfections in the optics, diffracting around the very mask designed to hide it. These artifacts have a certain signature, a way of behaving that differs from a true external source, and the team spent long hours modeling exactly what such artifacts should look like given the specific engineering of the instrument, given the specific orientation of the telescope during each exposure, given the specific thermal state of the equipment at the moment the light was gathered. And slowly, patiently, one by one, these explanations began to fall away. The signal did not match the expected pattern of background contamination. Its position, while not perfectly stable, did not drift in the way a distant, unrelated object would drift against the parallax of Webb's own orbital motion. It did not behave like scattered starlight either, lacking the particular smear, the particular symmetry that such artifacts tend to carry. Each test that should have dissolved the anomaly into something explainable instead left it standing, a little diminished perhaps, a little more uncertain in its exact parameters, but still present, still refusing to disappear. This is the moment in any such investigation where scientists begin speaking to one another differently, in more careful language, aware that they are approaching the edge of something that might matter. Emails between collaborating institutions grow longer. Calls are scheduled not to announce conclusions but to challenge them, each researcher taking turns playing the skeptic, the one whose job it is to find the flaw the others have missed. This adversarial collaboration, this internal culture of doubt, is not a flaw in how science operates. It is the entire point. Extraordinary claims survive only by surviving extraordinary attempts to kill them. Word of the anomaly did not, at this stage, reach the public. It existed only within the closed circuit of professional astronomy, in internal memos, in preliminary drafts not yet fit for submission, in the quiet, unglamorous back and forth of people trying to be right rather than trying to be first. There is a particular kind of tension in this phase of discovery, one rarely captured in popular accounts of how science works. It is not the tension of racing toward a finish line. It is the tension of standing very still, resisting the pull toward premature certainty, while something genuinely strange sits unexplained in front of you. Because here is what made this signal different from the earlier candidate detection, the one already logged, already debated, already treated with appropriate caution in the scientific literature. This new observation was not simply a repeat of that same faint smudge of infrared light. It showed subtle variations, small shifts in brightness across the different wavelength channels Webb is capable of measuring, shifts that did not correspond neatly to what a planet's reflected and emitted light should produce, nor to what a simple background contaminant would produce, nor to what any single known category of astrophysical object was expected to produce on its own. It was almost, some of the researchers admitted quietly to one another, as though they were looking at the combination of two things layered atop each other, two separate signals whose light had merged, by chance or by proximity, into something that resembled, at first glance, one anomaly, but which, upon closer inspection, seemed to carry the fingerprints of more than a single source. If true, this possibility would complicate everything. It would mean the earlier candidate, already uncertain, was not simply confirmed or denied by this new data, but rather entangled with something else entirely, something that no one on the team had anticipated needing to explain, and something that, once considered seriously, forced the team to reopen questions they had thought long settled about this particular corner of the sky. Because the truth is, no patch of space is ever truly empty, and no signal is ever truly isolated. Alpha Centauri does not exist in a vacuum of attention. It sits embedded within a galactic environment thick with drifting matter, faint clouds of interstellar dust, the occasional wandering body untethered to any star, the ordinary debris of a galaxy that has been forming and destroying worlds for over 10 billion years. Any one of these things, passing through the narrow cone of Webb's gaze at just the right moment, could contribute its own small trace of light to an already faint and fragile signal. The astronomers understood this. They had accounted for it in their models. And yet, accounting for a possibility in theory is different from watching it complicate your data in practice. So they began the slow work of trying to separate what might be layered together, treating the anomaly not as a single point of light, but as a puzzle that might contain more than one piece fused by distance and faintness into something that looked, at first, deceptively simple. This is delicate work, the kind that cannot be rushed without risking the introduction of bias, the temptation to see in the data whatever shape one is hoping to find. Astronomers have a name for this danger, a quiet, humbling term: confirmation bias, the tendency of the human mind to notice patterns that confirm what it already suspects and to overlook the ones that do not. Webb's own data reduction pipelines are built, in part, specifically to guard against this tendency, applying blind tests, withholding certain parameters from analysts until after their initial interpretations are locked in, forcing objectivity onto a process that would otherwise bend, almost imperceptibly, toward hope. And there was hope here, quiet and unspoken, the kind that scientists rarely admit to publicly but that hums beneath even the most rigorous analysis. Alpha Centauri is not just another star system. It is the closest one we have. If there is a planet there, especially one occupying a stable, temperate orbit around either of its two sun-like stars, it would represent something almost unbearably significant. A world near enough that future generations, centuries from now perhaps, might send instruments capable of resolving not just its presence but its atmosphere, its surface, perhaps even its chemistry, in far greater detail than we can achieve for any planet orbiting a more distant star. The stakes of this particular patch of sky have always been higher than the stakes of almost anywhere else astronomers have looked, precisely because of how close it sits to us, how within reach it feels even as it remains, by any practical measure, impossibly far. This is worth sitting with for a moment, because scale is difficult for the human mind to hold on to honestly. 4 light-years sound small when spoken aloud, especially set against the scale of the galaxy, which spans over 100,000 light-years from edge to edge. But 4 light-years is still nearly 25 trillion miles, a distance so vast that even light, the fastest thing in existence, takes over 4 years to cross it. Our fastest spacecraft, moving at speeds that would have seemed like magic to earlier centuries, would still require tens of thousands of years to make that same journey. And so even the nearest star system remains, for now, a place we can only study through the patient interpretation of light, never through direct contact, never through the simple certainty of arrival. It is this tension between nearness and unreachability, awe and humility, that shaped how carefully the research teams proceeded once they suspected the anomaly might not be a single, clean signal. They began running simulations designed to model what it would look like if 2 distinct sources, close together in angular separation but different in nature, were blended by the limits of Webb's angular resolution, the finest detail the telescope is physically capable of distinguishing at that distance. Even Webb, for all its extraordinary sensitivity, cannot resolve every possible pair of objects if they sit too closely together as seen from Earth. At the distance of Alpha Centauri, 2 sources separated by less than roughly the distance between Earth and the asteroid belt might still appear, from our vantage point, to occupy the same single point of light, their signals merging into something that looks unified but is not. If this were the case here, then the anomaly was not one mystery but 2, tangled together by distance and faintness, each contributing its own subtle signature to a blended signal that no single explanatory model could fully capture. This possibility, once raised, changed the entire framing of the investigation. It meant the researchers were no longer simply trying to determine whether a planet existed. They were now trying to determine how many separate things might be hiding within a single point of light, each one requiring its own explanation, its own model, its own painstaking verification, before anyone could say with confidence what, precisely, Webb had been looking at all along, and what, if anything, it meant for the two nearest sun-like stars in the sky. The simulations took weeks. They required computing resources that seemed almost absurd, devoted to a signal so faint it might dissolve into nothing under the slightest scrutiny, and yet this is what serious inquiry demands: the willingness to invest tremendous energy in something that might, at the end, turn out to be nothing at all. The researchers wrote code to generate synthetic observations, imaginary versions of what Webb would see if it were looking at various configurations of background stars, planets, dust clouds, and other astronomical objects layered at different distances behind Alpha Centauri A. They ran thousands of permutations, letting the computer explore the space of possibilities that human intuition alone could never map completely. And what emerged from these simulations was a kind of negative capability, to borrow the poet's phrase, the ability to sit inside multiple incompatible explanations without grasping at certainty. Yes, some configurations of background objects could produce a signal resembling what they had observed. Yes, a close binary pair of faint stars, aligned just so, could generate a light signature that mimicked some aspects of what Webb's instruments had captured. But other configurations, equally plausible from a purely statistical standpoint, would have produced different signatures, subtly but detectably different in ways that the data did not seem to support. The universe, it appeared, was narrowing the possibilities, but not to zero, and not to a clean, singular answer. It was during this phase that a researcher on one of the supporting teams, an astronomer whose primary expertise lay in the structure of stellar systems and the dynamics of planetary formation, made an observation that shifted the conversation in a direction no one had explicitly anticipated. She was reviewing the spectroscopic data, the way the light from the anomaly broke down across different wavelengths, looking for the particular chemical signatures that would mark it definitively as belonging to one category of object or another. And what she noticed was a subtle asymmetry, a hint of something in the infrared that did not quite match what a passive, orbiting object would naturally emit. In the simplest case, a planet orbiting close to a star would show a particular thermal profile. The side facing the star would grow hot, radiating excess energy in the infrared like a coal glowing in the dark. The far side would be cooler, starved of direct heat, cooler still in the shadow of the planet's own body. You could, in theory, model this heat distribution, predict what the thermal emission should look like, and compare it to observation. But the data Webb had returned showed something at least subtly different. The thermal profile was not quite what a simple equilibrium model would predict. It was as though something else was contributing heat, or absorbing it, or somehow disturbing the clean energy balance that should exist between radiation in and radiation out. This could mean many things. It could mean that the object, if it existed as a discrete body, had an atmosphere that was thickening, circulating, redistributing heat in ways that a bare rocky surface would not. It could mean that the light was being scattered by dust, that clouds of particles between the source and our instruments were meddling with the signal, adding opacity and complexity. Or it could mean something else entirely, something that the researchers had not yet thought to consider because it fell outside the standard categories they had all been taught to expect. The researchers sat with this asymmetry for days, running through mental catalogs of astronomical phenomena, asking herself what could explain a heat signature that matched no simple model. She did not announce her finding immediately. Instead, she prepared a presentation, assembled her analysis, and brought it to the collaboration's next full meeting, timed for an evening when enough team members across different time zones could gather, bleary-eyed or middle of the night, to engage with what she had found. What she presented was not a conclusion but a question, asked very carefully. What if the signal they were observing was not from a stable, settled object at all, but from something in transition, something that was actively changing? An object being formed, perhaps, out of the dust and gas surrounding Alpha Centauri A. A planetary embryo, still gathering material, still releasing gravitational energy as it condensed toward adulthood. Or something even stranger, a dust cloud that was not merely drifting passively but actively being heated by some dynamic process, stirred by gravitational tides or magnetic forces or some other mechanism that kept its material in agitated, chaotic motion. The implications of this suggestion hung in the digital silence of the video conference for a moment. If correct, it would mean that what Webb was observing was not a finished thing but a process, a moment captured in an ongoing sequence of cosmic events. It would mean that Alpha Centauri was not simply a system of mature stars with, perhaps, planets orbiting in stable configurations, but rather a system still actively busy with formation and evolution. It would mean that the faint signal, rather than being an anomaly to be resolved, was potentially a window into how worlds are actually built, how dust becomes rock becomes planet in the real universe, not in theory or simulation, but in observation of something happening in genuine, ongoing time. And once this possibility was raised, once the team allowed themselves to consider it seriously, they realized they had been asking the wrong questions all along. They had been treating the anomaly as either a planet or an artifact, when what they might actually be looking at was neither of these things but something in between, something caught in the act of becoming, something that refused to fit the tidy categories because those categories had been built from a universe of finished things, a universe of planets already formed and stars already settled into their long adulthoods, and had never been designed to hold something still wet with its own creation. Consider what this would mean, drifting here in the dark with the thought. Alpha Centauri is not young. Its stars are not newborns wrapped in the natal veils of dust that surround so many stellar nurseries. Alpha Centauri A and B are mature, aged somewhere near 6 billion years, older even than our own sun in some estimates, their light steady and unflickering in the way old light always is. By every convention of formation timelines, whatever planets they once built should have finished building long ago. The dust should have coalesced or dispersed. The chaos should have resolved into order, the way a storm resolves into calm water. This is what the models predict, what the equations of accretion suggest should happen within a few tens of millions of years of a star's ignition, a blink within a life of billions. And yet here, if the anomaly was what some now dared to imagine, was a process that appeared to still be running, quietly, faintly, long after it should have stopped. There are precedents for this kind of surprise, scattered through the archive of things astronomers thought they understood. Debris disks around mature stars, rings of collisional dust ground down from asteroids and comets in slow perpetual violence, have been found in systems far older than anyone expected them to survive. Fomalhaut, only 25 light-years distant, still wears a debris ring some 400 million years after its birth, a ring shaped and sculpted by the gravity of unseen planets, still catching starlight and scattering it outward for telescopes to find. The idea that planetary systems settle into permanence and then simply persist unchanged for the rest of their stars' lives has been eroding for years, replaced by a messier, more interesting truth. That planetary systems are dynamic for far longer than once believed, that collisions continue, that migrations continue, that the architecture of a system can still be rearranging itself even in what should be its old age. But what the Alpha Centauri data seemed to suggest, if the more radical interpretation held, was something even stranger than late-stage debris. It was not simply matter being ground down by ancient impacts. It was, potentially, matter still being built up, a signal consistent not just with destruction but with accretion, the slow gravitational gathering of small things into larger things, the very process that should have exhausted itself in the system's deep past. Some in the working group began to speak, quietly, in the careful hedged language scientists use when a thought is too large to say plainly, of a second-generation formation event. The idea that a collision between larger bodies, a planet or protoplanet shattering against another in some ancient orbital catastrophe, could have released enough fresh material to begin the accretion process anew, seeding a new round of building from the wreckage of the old. Not a system finishing its formation. A system reopening it. If true, it would not overturn the physics of planet formation so much as reveal a wrinkle in it that had never been observed so close, So clearly, in a system near enough for humanity's clumsy instruments to actually resolve. Formation from the collapse of a molecular cloud is the beginning most models describe. But formation from catastrophe, from the debris of destruction rather than the debris of birth, is a different kind of story, one written not in gentle collapse but in violence, in the aftermath of impacts, in the slow reassembly of ruin into something new. It would mean that a planetary system's timeline is not a single line running from chaos to order and then stopping, but something closer to a loop, or a spiral, capable of restarting itself under the right catastrophic conditions, capable of being young again in some small local sense even while its parent star ages on, indifferent, toward its own long twilight. And there was something almost unbearably intimate about this thought, something that pulled at the mind in the quiet hours of review, the way certain ideas do when the lights are low and the office is empty and there is no one left to perform composure for. Alpha Centauri is close. It is close in the way almost nothing else in the night sky is close, 4.24 light-years to Proxima, closer still in cosmic terms to the binary pair of A and B, near enough that its light left when human eyes were unremarkable animals wandering an African landscape, near enough that whatever process was unfolding there was unfolding within a whisper of astronomical scales, in our own galactic backyard, at the very system many future starships, if they are ever built, are already dreamed to be aimed toward. To find not a settled system but a system perhaps still remaking itself, perhaps still capable of the violence and creation that built worlds in the first place, was to find something almost too resonant to be comfortable, a mirror held up not to what planets once were, but to what they might still, quietly, and against every prediction, be becoming. And so the working group found themselves circling a single, quiet question, turning it over the way one turns a stone found on a beach, uncertain at first of its weight, its origin, whether it was shaped by something ordinary or something rare. If Alpha Centauri was indeed hosting a second-generation formation event, a rebirth of sorts kindled from ancient wreckage, then the anomaly they had detected was not a flaw in their instruments or a trick of light bent through interstellar dust. It was a fossil and a birth at once, a record of violence still legible in the debris, and a promise of something new condensing slowly out of that same violence, indifferent to the human eyes now watching from so many trillion miles away. There is a strange comfort in violence that becomes creation, though it takes a certain stillness of mind to feel it. Rock does not become planet gently. It is not the slow accumulation of kindness. It is collision after collision, fragment finding fragment in the dark, gravity pulling debris together only for larger impacts to sometimes blow it apart again, a churn of destruction and assembly that looks, from enough distance, almost like patience. The solar system itself, our solar system, the one cradling this fragile blue world with its oceans and its cities and its sleeping billions, was not spared this violence in its youth. The moon above us, pale and familiar, is thought by many researchers to be the frozen memory of just such a catastrophe, the product of a Mars-sized body named Theia striking the young Earth some 4.5 billion years ago, a collision so immense it reshaped both worlds, flinging molten debris into orbit that would slowly, over millions of years, gather itself into the moon that now pulls gently at every tide on every shore on this planet. Violence, in other words, is not opposed to the tenderness of a quiet ocean under moonlight. It is the hidden author of that tenderness, the thing that made the moon possible at all. If something similar had happened, or was still happening, in the debris around Alpha Centauri, then what the telescope had captured was not an aberration in the story of planet formation but a continuation of the very story that had, billions of years ago and 93 million miles from where these words are being spoken, made the moon, made the tides, made the conditions for water to remain liquid long enough for something like memory to eventually exist. The universe does not appear to build gently. It appears to build through cycles of shattering and reassembly, small violences accumulating into large stabilities, chaos slowly, almost reluctantly, becoming order. And to see this process, not inferred from ancient scars on ancient worlds, but happening now, in a system 4 light-years away, was to be given something almost too precious to hold quietly. It was to see, in something like real time, the machinery of creation still running, its gears still turning in the dark spaces between two ordinary stars. But there was a complication in this beautiful, terrible thought, one that some in the group raised carefully, almost reluctantly, aware that it might undo the fragile elegance they had only just allowed themselves to consider. A second-generation formation event requires, as its precondition, a catastrophic collision large enough to generate the debris necessary for renewed accretion. It requires, in other words, that something large already existed in that system and was destroyed. Not a formless cloud of primordial dust slowly coalescing for the first time, but a body, perhaps planetary in scale, perhaps only protoplanetary, that had already achieved some meaningful mass before being obliterated. This raised an unsettling implication that no one wanted to say aloud at first, though it moved through the group like a current beneath still water. If such a collision had occurred, it meant that Alpha Centauri had once possessed, and then lost, something like a fully or partially formed world. It meant that somewhere in that system's long and largely unwitnessed history, a planet, or something enough like a planet to matter, had existed, and had been destroyed, its substance scattered into the very rings of debris the telescope was now studying with such fragile hope. There is no way, yet, to know what such a world might have been. Whether it orbited close to its star in the scorched inner regions where temperatures climb high enough to melt stone, or farther out in colder reaches where ice rather than rock might have dominated its composition. Whether it was barren from the start, a lifeless accumulation of minerals and metal, or whether, in some far more delicate scenario that no one in the room was yet willing to speak into existence, it might have held conditions gentle enough for something to have begun, something small, something early, something extinguished before it had the chance to become anything the universe would later call life. This thought, once raised, could not be unraised. And the room grew quiet in the particular way rooms grow quiet when everyone present understands that the conversation has crossed, without warning, from astronomy into something that borders, however faintly, on something closer to grief, or perhaps something closer to reverence, the two feelings sitting so near each other in the chest that it becomes difficult, in certain quiet moments, to tell them apart. No one in the group was foolish enough to claim they had found evidence of life, or even evidence of a world capable of it. The data did not permit such a leap, and every scientist present understood the difference between a hypothesis worth investigating and a story worth telling around a fire. And yet the mind, once it opens a door, finds it difficult to close again. To imagine a body large enough to matter, orbiting one of the two suns of Alpha Centauri, existing for some span of time, whether millions of years or merely a cosmic instant of a few 100,000, and then to imagine that body ending, not through the slow entropy of stellar aging but through sudden and total collision, was to imagine a kind of death that has no analog in human experience. It is not the death of an organism. It is the death of a place. The unmaking of whatever geography it might have carried within it, whatever chemistry, whatever silence or storm. A place erased so thoroughly that its only remaining trace, 4 1/3 light-years later, is a faint gravitational flicker and a smear of infrared light too dim to be certain of anything at all. There is a particular kind of humility that settles over people who study the universe long enough, and it has less to do with human insignificance than most assume. It is not that we are small, though we are. It is that the timescales involved make our entire species feel like a held breath, a single frame in a film that has been running for 13.8 billion years and will run for trillions more after the last human eye has closed. Whatever happened to that hypothetical world around Alpha Centauri, if it happened at all, likely happened long before the first single-celled organism divided in Earth's ancient oceans. It may have happened before Earth itself had finished cooling from its own molten youth. The debris the James Webb Space Telescope detected is not a memory in any sentimental sense. It is simply matter, indifferent matter, still following the same laws of gravity and momentum that it followed in whatever violent moment first flung it into its current slow drift. And yet it is difficult, gazing at this data from the distance of a species that only recently learned to ask questions about any of it, not to feel something like tenderness toward that vanished body, whatever it was, wherever its pieces have since scattered. The research team, in their published notes and in the careful language of peer review, tried to strip this tenderness away, tried to reduce the finding to its measurable components. An excess of thermal emission inconsistent with known debris disk models, a possible signature of ongoing accretion, a mass estimate too uncertain to be called a discovery so much as a direction for future observation. This is how science protects itself from its own wonder, wrapping awe in the language of error bars and confidence intervals, not because the wonder is unwelcome, but because wonder unchecked has led astronomers astray before, has produced canals on Mars that were never there, has produced faces in rock formations that were only shadow and expectation. The caution is not coldness. It is a kind of discipline learned the hard way, an acknowledgement that the universe rewards patience and punishes certainty, and that the most honest thing a scientist can say, most of the time, is simply, "We do not yet know, but we are looking closely, and we will keep looking." Still, in the private conversations that happen after the papers are drafted and the press releases are cautious, in the hallway exchanges and the late-night messages between colleagues who have spent decades staring into the same patch of sky, something less guarded slips through. Because Alpha Centauri is not simply another entry in a catalog of thousands of stars now known to host planets, another data point in an ever-growing census of exoplanetary systems scattered across the galaxy like grains of sand flung across a beach no one will ever fully map. It is the nearest star system to our own. It is the place human imagination has turned toward for centuries when it dreamed of somewhere else, some other shore beyond the solar tide, some possible destination for whatever version of humanity eventually builds the ships capable of crossing such a distance. To learn that this particular system, of all the systems in the sky, might still be in the process of violent, unfinished formation, might still be capable of the same planetary genesis and planetary death that shaped our own solar system in its infancy, is to feel the nearness of the universe in a way that few discoveries ever manage. It is not a distant abstraction. It is the closest possible mirror, and mirrors, as anyone who has stared into one too long in the dark knows, have a way of showing you more than you expected to see, more than you were entirely prepared to find, and the researchers, whatever their careful language in daylight, were not immune to this particular vertigo in the privacy of their own late-night thoughts. Consider, for a moment, the instrument itself, the James Webb Space Telescope, hanging in its slow procession around the second Lagrange point, nearly 1,000,000 miles from Earth, farther than the Moon, tucked into a gravitational balance point where sunlight and shadow hold each other in perfect equilibrium. It took decades to build, cost billions of dollars, was delayed so many times that entire careers were spent waiting for its launch, scientists who began as graduate students retiring before its mirrors ever unfolded in the cold vacuum of space. And now this instrument, this impossibly patient piece of human engineering, gold-plated and sun-shielded and cooled to nearly absolute zero so that its own heat would not blind it to the faint infrared whispers of the universe, had turned its attention toward a system so close, astronomically speaking, that it barely qualified as a target at all by the standards of a telescope built to stare toward the very edge of observable time. And yet in doing so, it may have found something the more distant searches never could, something too subtle, too faint, too delicately balanced between signal and noise to have been visible except at this proximity, with this precision, at this particular moment in the long patience of the instrument's operation. There is something worth sitting with in that fact alone. That the greatest tool ever built for staring into the deep past of the universe, for capturing the light of galaxies so distant their photons have been traveling since before the Earth existed, found something remarkable not at the edge of everything, but nearly in our own front yard. It is as if a telescope built to read the oldest books in the library turned, almost by accident, to the book sitting closest on the shelf, and found its pages were not finished being written. There is a lesson in this, though it is not one that fits easily into any single sentence. Something about how proximity does not equal familiarity, how the nearest things are sometimes the least understood precisely because they have always been assumed to be settled, catalogued, closed. Alpha Centauri has been observed by human eyes and human instruments for centuries. It was among the first stars whose distance was measured with any confidence, back in the 19th century, when astronomers first began to grasp the staggering scale of interstellar space by watching this very system shift, almost imperceptibly, against the backdrop of more distant stars as the Earth traced its orbit around the Sun. It has been a fixture of astronomical study for so long that it might reasonably have been considered, by the early 21st century, a solved problem: 3 stars, 2 of them sun-like and orbiting each other, the third a dim red dwarf drifting farther out, its planet Proxima be announced with great excitement in 2016, its atmosphere and habitability still debated in careful, ongoing terms. And yet solved problems have a way of quietly refusing to stay solved, particularly when the instruments used to study them improve by orders of magnitude, particularly when a telescope capable of detecting the heat signature of a bumblebee on the surface of the Moon, to use the comparison so often reached for by those trying to explain Webb sensitivity to audiences unfamiliar with infrared astronomy, is finally pointed toward a system whose secrets had, until now, been hidden simply because no one had ever looked closely enough, or in the right wavelength, or with enough patience to notice. This is perhaps the quietest and most humbling lesson embedded in the entire finding, more humbling in some ways than the anomaly itself. That the universe does not reveal itself all at once, does not surrender its secrets in a single grand unveiling, but rather offers them slowly, reluctantly, to whoever returns again and again with better tools and more patience, willing to look at the same patch of sky 1,000 times if that is what it takes to finally notice the one detail that changes everything. The Alpha Centauri system, then, is not merely a stellar neighbor whose planets we are cataloging out of proximity and convenience. It has become, in the wake of this anomaly, something closer to a proving ground, a place where the assumptions of an entire field are being quietly tested against the stubborn, indifferent reality of actual observation. Every model of planetary formation, every simulation run across supercomputers modeling millions of years of gravitational interaction in mere hours of processing time, every textbook diagram showing the tidy progression from protoplanetary disk to rocky world, must now contend with the possibility that reality is messier, more recursive, more capable of surprise than the models allowed. And this is, perhaps, the most unsettling implication of all, more unsettling even than the thought of a shattered world or a violent birth still underway. It is the quiet recognition that certainty, in this line of work, was always a kind of borrowed comfort, a story astronomers told themselves in the gaps between what the instruments could actually see and what the mathematics insisted should be there. For decades, the search for a planet around Alpha Centauri A had been an exercise in exquisite frustration, radial velocity surveys straining to detect the almost imperceptible wobble a world might induce in its star, a wobble measured in centimeters per second, smaller than a human walking pace, buried beneath the roar of stellar noise. The churn of convection cells the size of continents rising and falling across the photosphere, the faint pulse of magnetic activity that mimics and masks the very signal researchers are trying to isolate. And then, in the thermal infrared, where the James Webb Space Telescope's coronagraph could finally suppress the blinding light of the star itself, a signal appeared that should not have appeared, a faint point of warmth sitting almost exactly where a planet in the habitable zone would be expected to sit if such a planet existed at all. The astronomers who found it did not celebrate. This is worth pausing on, worth letting settle into the quiet of the mind like snow accumulating on a windowsill. They did not announce a discovery. They announced a candidate, a possibility, a thing that might vanish under further scrutiny the way so many candidate signals have vanished before, revealed as instrumental artifacts, as background contamination, as the ordinary trickery of light bending through cold optics across 68 astronomical units of interplanetary vacuum. Because the alternative to a planet is almost as strange as the planet itself would be. The alternative is a disk of dust, fine and diffuse, warmed by starlight, arranged in some configuration around Alpha Centauri A that no one had modeled, no one had predicted, a haze of material that should not persist in a system as old and as gravitationally worked over as this one. 4.5 billion years of orbital mechanics, having had ample time to either accrete such debris into larger bodies or scatter it into the interstellar dark. Consider what that means. Consider that the two competing explanations for this anomaly are, in their own ways, equally unsettling. If it is a planet, then something in our understanding of formation timelines, of migration patterns, of the survivability of worlds in a binary system where a second sun's gravity should be sculpting and disrupting the outer disk on geologic timescales, is incomplete in ways that ripple outward to every other system we have ever modeled. And if it is dust, then we are looking at a mechanism of replenishment, some ongoing process still generating fine particulate matter in a system old enough that such processes should have ceased eons ago, some quiet collision still happening, some reservoir of icy bodies still grinding against each other in the dark beyond what our telescopes can resolve, a debris disk behaving like a younger system's disk, echoing the violence of formation long after formation should have finished its work. The instrument responsible for this observation, the mid-infrared instrument aboard James Webb, was built to peer through exactly this kind of veil, tuned to wavelengths between 5 and 28 microns, where the glow of warm dust and the faint thermal signature of a young or temperate planet both become visible against the suppressed glare of the parent star. But the coronagraph, for all its precision, works by blocking starlight rather than eliminating it entirely, and what remains is a residual smear of scattered photons that must be subtracted, modeled, and subtracted again, a process of digital archaeology performed on images that contain, at most, a handful of photons distinguishing signal from noise. The astronomers speak of this in careful, hedged language, phrases like consistent with, phrases like cannot be ruled out, phrases that carry the particular humility of people who have been burned before by signals that seemed real and were not, and who understand that Alpha Centauri, of all systems, deserves more skepticism than most, precisely because it matters more than most, precisely because our nearest neighbor is the one place where a false claim would echo the loudest and do the most damage to the credibility of an entire discipline. And yet the signal persists across multiple observations now, reappearing in follow-up imaging with a consistency that pure noise should not produce, sitting in roughly the same location relative to the star, at roughly the same brightness, across observing windows separated by months, each new epoch either confirming the pattern or complicating it further. The astronomers themselves seeming to hold their breath between data releases the way a person might hold their breath waiting for a diagnosis, hoping for clarity, bracing for ambiguity instead. Because that is what the universe has offered here, again and again, at this system that once seemed so simple, so nearby, so almost knowable. Not an answer. Not yet. Only the accumulating weight of a question that refuses to resolve. A signal that behaves like something real without yet consenting to be confirmed as anything at all. There is a particular kind of patience required for this work, a patience that has little precedent outside of astronomy, or perhaps outside of geology, outside of the disciplines that have made peace with timescales too vast for a single human career to encompass. The team studying this signal will likely spend years confirming or disproving what a first glance suggested in a matter of hours. They will request more observing time from a telescope so oversubscribed that every hour of its attention is rationed like water in a drought, weighed against the competing needs of 1,000 other research programs, each convinced of its own urgency. And even when that time is granted, even when the data arrives, the interpretation will not resolve quickly, because the universe does not owe us clarity on any schedule we might prefer. It offers only the data, cold and indifferent, and leaves the meaning-making to us, fallible creatures pattern-matching against noise, hoping our instruments are steady enough and our models honest enough to tell the difference between discovery and wishful thinking. Consider, too, What it means that this uncertainty sits inside a system so achingly close, in cosmic terms, that its light left home only 4 years before arriving here. 4 years is nothing. It is less than the span of a single undergraduate degree, less than the ordinary drift of a career, and yet it is enough distance that no spacecraft humanity has ever built could reach it within a lifetime, enough distance that the photons Webb captured had already been traveling since before the telescope itself existed, since before its mirrors were ground and polished and folded into a rocket fairing, since before the idea of it was fully formed in the minds of the engineers who built it. The system is close enough to feel like a neighbor and far enough to remain, in every practical sense, unreachable, a place we can only know through the second-hand testimony of light, translated and retranslated through instruments, algorithms, and the fallible judgment of the people reading the output. And this is where the unsettling quality of the whole endeavor deepens further, because the very telescope making this observation possible is itself a fragile, singular thing, unrepairable in any traditional sense, parked at the second Lagrange point nearly 1,000,000 miles from Earth, beyond the reach of any servicing mission the way the Hubble Space Telescope was serviced across 3 decades of shuttle flights. If something fails in Webb's delicate architecture, the 18 gold-coated beryllium mirror segments unable to be adjusted, the sunshield's 5 gossamer layers unable to be patched, there is no rescue, no replacement, only the slow silence of an instrument going dark, its remaining observations forever incomplete, its mysteries handed down half-answered to whatever telescope comes next, whatever decade that might be. Every observation of Alpha Centauri, every hour spent staring at that ambiguous thermal glow, is therefore also a kind of race against entropy, against the eventual and inevitable failure of hardware operating far past the reach of a wrench or a spare part, a race the astronomers do not speak about openly but which surely colors the urgency beneath their careful, hedged language. There is something almost devotional in this, something that resembles faith more than it resembles the popular image of science as cold certainty stacked upon cold certainty. The researchers continue collecting data not because they know what they will find, but because the not knowing itself has become a kind of calling, a commitment to sit with ambiguity long enough that it might, eventually, resolve into understanding, or might instead resolve into an admission that the signal was never there at all, that the warmth they saw was a trick of scattered light, a phantom born of imperfect calibration. Both outcomes are treated with the same rigor, the same reluctance to declare victory prematurely, because in this field, being wrong in public carries a cost that outlasts any single career, a cost measured in eroded public trust, in headlines that promised a second Earth and delivered, months later, a quiet retraction that receives a fraction of the attention the original announcement did. And so the story of Alpha Centauri, as it stands today, is not a story with an ending. It is a story suspended in the middle of itself, caught in the same recursive uncertainty that seems to characterize every corner of the system once we look closely enough, the shattered world hypothesis around Alpha Centauri b, the anomalous debris or possible planet around Alpha Centauri a, the outer gravitational tug of Proxima Centauri still working its slow influence on the inner binary across geological time. Each thread on its own might be dismissed as an interesting anomaly, a statistical fluctuation, a footnote in an otherwise well-behaved planetary system. But taken together, woven into the same tapestry of observation, they suggest something larger, something that unsettles not because it points to danger or violence, but because it points to a fundamental incompleteness in how we imagine the birth and death of worlds, an incompleteness that the nearest star system to our own has chosen, almost mockingly, to reveal first, as if daring us to look closer, before we dare to look farther. And perhaps that is the quiet lesson embedded in all of this, one that has nothing to do with alien civilizations or catastrophic collisions, and everything to do with humility, the kind of humility that comes only from proximity, from having a laboratory close enough to interrogate in detail rather than a smudge of light glimpsed once and never resolved again. Most of the exoplanets humanity has catalogued, the roughly 6,000 confirmed worlds orbiting distant suns, exist for us only as statistics, a dip in brightness during a transit, a wobble in a spectral line, a handful of derived parameters, mass, radius, orbital period, entered into a database and rarely revisited with the same intensity twice. Alpha Centauri does not permit that kind of distant, statistical relationship. Its proximity insists on scrutiny, insists on return visits, insists that every anomaly be chased down rather than filed away, because unlike almost every other system in the sky, this one might, within a generation or two, actually be visited, if not by human hands then by the fragile robotic emissaries already being imagined, laser-driven sails no larger than a postage stamp, accelerated to a fraction of the speed of light by ground-based arrays of lasers more powerful than anything yet built, arriving in perhaps 20 years to send back, decades later, a handful of photographs taken during a flyby lasting mere hours. This is the audacious promise behind projects like Breakthrough Starshot, a promise that remains, for now, more engineering fantasy than engineering fact. The technology for a laser array of the required power is still theoretical, the miniaturized sail and sensor package still a concept sketched on whiteboards rather than assembled in a clean room. But the fact that such a mission is even conceivable, that serious scientists gather at serious institutions to debate the feasibility of interstellar flight aimed specifically at the system and no other, reveals something about how differently we hold Alpha Centauri in our collective imagination. It is not merely data. It is destination. It occupies a category of its own, suspended between the abstraction of distant astrophysics and the concrete, almost geographic reality of a place one might someday travel to, however many decades that journey might require, however many generations of scientists might live and die in the interval between launch and arrival of the first images. And so when the anomalies accumulate, the shattered debris ring, the ambiguous thermal signal, the long gravitational shadow cast by Proxima across billions of years, they carry a different emotional weight than similar anomalies would carry if found around a star 100 light-years distant. They feel less like curiosities and more like foreshadowing, previews of what future missions, whether robotic sails skimming past at a significant fraction of light speed or some more advanced successor to web peering even deeper into the infrared, might eventually confirm in exquisite, undeniable detail. We are, in a sense, reading the opening pages of a story whose fuller chapters may not be written for another 50 or 100 years, and the strange, unresolved quality of what we have gathered so far, the missing debris, the tentative planet that may or may not exist, becomes less a source of frustration and more a kind of invitation, a reason to keep looking, keep funding, keep building the instruments capable of resolving what remains stubbornly blurred. There is also, within this, a meditation on scale that is easy to overlook amid the technical detail. 4 light-years is nothing to the galaxy, a rounding error in a disk of stars roughly 100,000 light-years across, itself one of perhaps 2 trillion galaxies scattered through the observable universe. And yet 4 light-years is everything to us, the entire practical horizon of what might someday be physically reachable, the difference between a system we can dream of visiting and the overwhelming majority of the universe we can only ever observe, frozen at whatever distance in time the light happened to depart, forever a message from a past we cannot answer. Alpha Centauri sits at the exact threshold where astronomy shifts from the purely contemplative to something almost tentatively practical, and that threshold status may be precisely why its anomalies feel so significant, so worth returning to again and again with instruments as precious and irreplaceable as the James Webb Space Telescope. Because if the models are wrong here, in the one system close enough to eventually check our answers against physical reality, then the implications ripple outward to every other system we have ever modeled with the same assumptions, the same simulations, the same tidy diagrams of disk evolving into planet evolving into stable, mature system. Alpha Centauri, in this sense, has become something like a control group for the entire discipline of exoplanetary science, a place where theory finally meets a target close enough that theory cannot hide behind distance and can be tested rather than merely inferred, and it is beginning to look, more and more, as though the theory does not entirely hold, as though there is something about binary star systems, something about the long, complicated gravitational choreography of 2 suns locked in mutual orbit that we have not yet accounted for, something that may explain not only what is happening here at Alpha Centauri, But what is quietly happening in countless binary systems scattered across the galaxy, systems we have too often treated, in our models, as simple variations on the single star case rather than as fundamentally different environments with their own distinct physics of formation and survival. Consider the numbers for a moment, not as abstractions but as a kind of quiet reckoning. Something on the order of half of all sun-like stars in the galaxy exist not in solitude, but in the company of at least one companion, bound in gravitational partnerships that stretch across distances ranging from a few million miles to many billions, some pairs so close their outer atmospheres nearly touch, others so wide that an orbit might take hundreds of thousands of years to complete a single circuit. And for decades, the search for planets deliberately excluded many of these systems, not out of theoretical conviction that planets could not form there, but out of practical necessity, because the gravitational complexity of a second star introduces noise into every detection method, distorts the clean periodic signals that radial velocity and transit surveys depend upon, and so the census of known exoplanets skews heavily toward single stars simply because single stars are easier to study, an observational bias masquerading, for years, as a natural feature of planet formation itself. Alpha Centauri complicates that bias in the most direct way possible, because here, in the nearest possible laboratory, planets seem to exist anyway, seem to be forming or surviving or perhaps disintegrating under conditions that a generation of theorists once considered marginal at best, hostile at worst. The gravitational tides exerted by Alpha Centauri b on any planetary disk around Alpha Centauri a, and vice versa, should theoretically truncate the outer edges of each star's protoplanetary disk, stripping away material that might otherwise coalesce into gas giants at wide orbital distances, confining planet formation to a narrower, more crowded region closer to each star where gravitational perturbation is less severe. This is not idle speculation. It is the product of simulations run specifically to model binary star formation, simulations that predicted, with reasonable confidence, that terrestrial planets could form in the inner region of such a system, but that the process would be more violent, more prone to disruption, more likely to produce partial worlds, failed worlds, worlds assembled and then partially unmade by the endless gravitational tug-of-war between two suns that never fully agree on how the material between them should behave. If that shattered debris ring around Alpha Centauri b is real, if it is genuinely the wreckage of a planet or protoplanet torn apart, rather than material that never coalesced in the first place, then it may represent the first direct observational confirmation of exactly this predicted violence, a smoking gun for binary disruption that theorists have modeled mathematically for years but never actually witnessed with their own instruments. And if the thermal anomaly around Alpha Centauri a does turn out to be a planet, a world sitting improbably within the habitable zone of a star locked in gravitational combat with its neighbor, then it suggests the opposite lesson entirely, that terrestrial worlds can survive this violence, can find some stable configuration even amid the chaos, can persist despite everything the mathematics says should tear them apart. Both possibilities, existing simultaneously in the same small patch of sky, would mean that binary systems are not simply more hostile versions of single-star systems, but places where formation and destruction occur in tandem, in a delicate and largely unpredictable balance that our current models can gesture toward but not yet reliably forecast. This is the deeper implication rippling outward from those two small, ambiguous signals, an implication that reaches far beyond Alpha Centauri itself, because if half the sun-like stars in the galaxy exist in binary or multiple systems, and if those systems behave in ways meaningfully different from what our single-star-derived models predict, then an enormous swath of the galaxy's planetary census, the true accounting of how many worlds exist and what conditions shape them, remains essentially unmapped, hidden behind the observational bias that made binary systems harder to study and therefore easier to set aside. We may have been, without quite realizing it, constructing a picture of planetary formation using only the simpler half of the available data, mistaking convenience for comprehensiveness, and calling the result a general theory when it was, all along, a special case. There is something quietly humbling in recognizing this, something that recontextualizes the entire preceding chapters of this story: the shattered world, the anomalous thermal glow, the aging debris that should not persist but somehow does. None of it, perhaps, was ever really about Alpha Centauri specifically, not in isolation. It was always, in some sense, about the limits of what a single, convenient category of star system could teach us, and about how the closest possible example of a more complicated category was waiting, patiently, for light years away, ready to overturn assumptions the moment we built an instrument sensitive enough to actually see it clearly enough, patiently enough, to notice the exception hiding in plain sight, for light years from a species that had spent centuries assuming its own solar system was the template rather than one particular outcome among countless possible configurations. It is worth pausing here, at the edge of this long meditation, to hold two truths at once, the way this entire story has asked us to hold two truths at once from its very beginning. The signals described across this account, the debris that may be a shattered world, the thermal glow that may be a planet, remain, as of this telling, unconfirmed, provisional, held at arm's length even by the researchers who found them, exactly as good science demands. They are not yet facts inscribed in the textbooks. They are questions, sharpened and specific, waiting on further seasons of observation, further hours rationed from an oversubscribed telescope, further years of careful, patient, unglamorous work before anyone can say with confidence what lies in that faint infrared glimmer near our nearest stellar neighbors. And yet the other truth, sitting quietly beside the first, is that the mere existence of these open questions, sustained across repeated observation rather than dismissed as noise, already tells us something real and already confirmed, which is that the tidy story of planetary formation we once told ourselves, disk collapsing neatly into star, leftover material spiraling neatly into planets, worlds settling neatly into stable, permanent orbits, was always an approximation, a first draft, a simplification necessary for building models at all but never mistaken, by the honest scientist, for the full and final truth. This is not a cause for despair. It is closer to the opposite. A universe that behaved exactly as our early models predicted would be, in its way, a smaller universe, a universe already fully mapped, its mysteries exhausted before we had even finished building the instruments capable of investigating them. What Alpha Centauri offers instead, whatever its ambiguous signals eventually resolve into, is evidence of a cosmos still capable of surprising the people devoted to understanding it, still capable of returning data that does not fit cleanly into the frameworks built to receive it, still capable of insisting, gently but firmly, that there is more here than we assumed. That is not a small gift. In a universe of nearly incomprehensible scale, where most of what exists will remain forever beyond our physical reach, the discovery that our closest neighbors still hold open questions is a reminder that wonder does not require distance. It does not require a new frontier 1,000 light-years away. It can be found 4 light-years from home, in a system whose light left before this telescope existed, patiently waiting all that time to reveal something we had not thought to expect. And so we return, in closing, to that binary system hanging in the southern sky, 2 suns bound together in a slow gravitational dance stretching across roughly 80 years, a third small companion drifting far beyond them in an orbit so vast it may take 500,000 years to complete, and somewhere among them, still uncertain, still unconfirmed, the faint suggestion of worlds, whole or shattered, stable or still forming, real or merely a trick of scattered starlight not yet fully subtracted from the data. We do not know tonight which of these possibilities will prove true. Perhaps by the time future observations settle the question, the answer will feel almost anticlimactic, a debris disk after all, ordinary in its own way, or a planet confirmed and then, over years, rendered mundane the way even the most extraordinary discoveries eventually become simply part of the accepted record. Or perhaps the answer will remain strange for a long time yet, resistant to easy categorization, a permanent asterisk in the astronomical literature, a reminder written into the data itself that some corners of even our nearest neighborhood refuse to be fully known. Either way, the not knowing has already done its work. It has already reminded an entire field, and perhaps reminded anyone listening in the dark tonight, letting this story settle slowly over the hours before sleep, that certainty was never the only currency worth pursuing. There is a particular kind of peace available in accepting that the universe is larger and stranger than any model built to explain it, that even our closest, most familiar-seeming neighbors still carry secrets we have not yet earned the right to fully understand, and that this incompleteness is not a failure of the science but the very quality that keeps it alive, keeps the telescopes pointed outward, keeps the long patient work continuing across careers and decades. 4 light-years away, 2 suns are still turning around each other in the dark, indifferent to our need for answers, and somewhere in that turning, quietly, something remains unresolved, waiting, as it has waited for billions of years already, for us to finally understand what we are seeing.